First, the final exam. So we agreed. So final. So the 13th of January, as you suggest. 4 o'clock, so 4 to 6, 2 hours. I'll show you. If we have time, I'll show you a typical exercise. I mean, in the same format that how they are going to be. But today I want to finish up talking about Hamilton-Jacobi. But first I want to explain a few things about periodic motion. That's an important concept. I already said something when we talk about the Kepler's problem, right? Very often you are not so much interested, say, if you are discussing the motion of planets, right? The real problem may not be to find exactly the trajectory of a planet, but some more general property like the period, right? You want to know, for instance, what is the period of, say, Jupiter or some other planet going about the Sun. So this is the study of systems that move periodically on the same trajectory. And you want to understand a little better this. And I draw, let me just say if I stay in one dimension, so that my phase space is just two-dimensional, right, so that I can draw it on the blackboard, and I only have one generalized coordinate and one generalized momentum, right, and my Hamiltonian then is going to be something like this, right? And let's assume that the energy is conserved, and therefore my Hamiltonian, it is also the. So what is a periodic motion? You see, you can solve this equation, and therefore you have P, your generalized momentum, that is some function, well, let's write it like this, is a function of the coordinate and this constant that is the energy that is going to depend on the initial conditions. So you see in phase space, you can draw your system. Well, this is a one-dimensional, so it's very simple. And you understand that by periodic motion, you have something like this, right? You start from somewhere, and then you come back, and then back, and then back, and then back. Okay? And actually, in this, when you discuss periodic motions, you can, this is a closed periodic motion, like, so the orbit is closed, and usually this is called a libration. So meaning that you come back after a certain period, you come back exactly where you were, and you keep on moving. But you can also have something like, so here is P, and this is Q. And similarly, this is the phase space. But you can also have a periodic motion more like this, that you move back and forth, but one of the coordinates keeps on increasing. This is more what you call a rotation. Okay, just in case you. And actually, there is a simple example that I sort of mentioned already when we discussed the pendulum, right? Because for the pendulum, so this is the ideal one-dimensional system, right? So write the energy for a pendulum. What is it? Let's write so you want to write the Hamiltonian for a pendulum, right? Remember, you write so we have as coordinate, we take theta, so this is a pendulum, right? And the energy is going to be the kinetic energy, so it's going to be the square of the momentum conjugated to your generalized coordinate, right? Usually, if this is L, you have 2m. And then minus, in this case, the potential energy, right? So just mg L, and if you take this angle, the cosine of theta, okay? So this is an example of a one-dimensional Hamiltonian that I wrote that way. And you see, I can draw the phase space of this system, the phase space of this. Well, maybe I should. So you see, to draw the trajectory in phase space, you need to know p as a function of q, right? So here you need to know p theta as a function of theta. So let's solve this. I mean, it's trivial. You see that p theta is the square, well, plus or minus the square root. So you take on the other side. So you have 2ml square that multiplies E plus now the potential energy. Okay. And how do they look? So now I can draw as I did here. So here I have p theta, right? And here I have theta. And you see that indeed you can have both vibrations and rotations because it depends. You see, in a way, you have a rotation if you have some bounds on the range of your theta, right? And you see that actually you do have, because, well, it depends on say, if the energy, if this is less than mgl, right? If the energy is less than this potential energy, this maximum potential energy, then you see that because this is now, you see, this is less than this, and the cosine of theta can go from +1 to -1, so you do have a condition because you want this quantity to be real, right? So you see that you can solve this, you have a sort of cos theta max, right? That is, it is what? Is minus E divided by mgl, right? So you want to stay within that in such a way that this quantity remains. So because you have a sort of Q max, right, then your motion is bounded, and you are in this libration case, and what it looks like something like this. So there are circles. You see, there are circles, and they are like this. But on the other hand, you also, if the energy, on the other hand, is larger than mgl, then this quantity is always well defined. And so you also have the other, you know, you have something like this, that are the rotation solution. So this is when it goes around all the way, right? The other one is the small oscillation. So this is the diagram in phase space. Actually, you have also limiting solution like this, right? Where you cross exactly here. These are the case in which E is exactly equal to mgl, right? And here you have pi. Okay, so this is the way you draw your phase space, or better, you draw the motion of your system in phase space, and you see it carries some relevant information. I mean, this is simple because it's one dimensional, so you can draw it easily. But of course, if the system has more degrees of freedoms, it's still a point, but now the space is much bigger, so it's harder to okay. Now, if you have a periodic motion, you will see that if the motion is periodic, very often it's useful to introduce new variables that we are going to use. And one of these two variables is called big J. It's called the action variable. And it's simply defined as the line integral around the path, okay, of the P dq, okay? So you integrate your P along a complete period. So, like, this is the path that you integrate along. You will see well, in half an hour why they are useful. They are useful because they help us to compute the period of some system. For instance, here you want to find out the period of the pendulum, but you are not interested in solving the full differential equations and find the trajectory. You only want to find out what the period of a given pendulum is. You will see that by using this variable, you can do that without having to solve the differential equation. So that's why. For instance, let's. What is the action variable for the harmonical oscillator, right? Just like a pendulum when I take this at small angles. You remember that the P for the, the momentum of a harmonical oscillator, we computed on Monday, I think, or even the day before. Maybe, yeah. Right, the Hamiltonian was this. Right? Where omega is the usual square root of k over m. So you see the moment, you from this, exactly as for the pendulum, that they are very similar systems, you can get your P, right? The P is just the square root of 2me minus this term here, that is minus 2me, m square, omega square, q square. So what is the action variable for the pendulum? So I have to take the integral over a period of my, not the pendulum, the harmonical oscillator of P. So P is this thing I wrote here. So I take 2me minus m square, omega square, q square, and I have to integrate over q over one oscillation of your harmonical oscillator. And this is easy to, because remember that the solution, you can write the solution like 2e over m omega square, the sign of some omega t plus gamma, but essentially it's just I can call this just a angle variables, and then I integrate from 0 to 2 pi, right? So this integral becomes the integral from 0 to 2 pi. Now I have q square. Now notice that when I put the square, I get, right, the same factor 2e, well, 2e divided by omega, right? And then I get 1 minus sine square. 1 minus sine square. Did I do that right or not? 2. So now I'm not sure I did it right. I get 2e m omega square. So m. Okay, now I'm stuck. Yeah, 2, so I have 2me, right? Okay, so now I don't remember how to. So over a period, so I change. Okay, so then is 2me, I guess, right? Uh, uh, no, my omega square is right. So it's 2me. So then wait, but then dq, right, is again 2me divided by m omega square, right? There is a minus, then cosine theta that becomes square d theta, okay? M omega square, no, it's just the dq. dq is this constant, right? With the minus, no, without the minus, cosine theta d theta. So 2m, so m, 2e, okay, sorry. So 2e, so I have 2e, right, m divided by omega, okay. The integral over 2 pi of the cosine square theta d theta, okay, sorry. It has been a long day. Now that integral is pi, right? So I get 2 pi e divided by omega. So this is the value of my action variable for the harmonical oscillator, right? So what I'm going to do with this painfully rederived result? You see, I can, so now go back to the Hamilton-Jacobi, right? You have this characteristic function that was a function of q, and I call it alpha, but alpha that is equal to e, right, in this. And you see, I can, what I'm saying that now I want to change my, instead of having alpha, that was the momentum also, I go to W of Q and J. So I'm doing a sort of canonical transformation from Q alpha to new variables, the first of which I take this action variables, okay? And you see that I can introduce a new variable. Unfortunately, this is called little w. That is hard to distinguish. So this is little, and this is big. This is the characteristic function in the Hamilton-Jacobi, and this is a new variables that is called, so it's defined as, if you wish, the conjugate. So w, now this is big, so I should make it really big, with respect to j. And this is called the angle variable. So you see, I've defined two new canonical variables, the action and the angle variable. Okay? And what is interesting about this this is the equation of motion of this one, the little one. So I take the little one dot, right? It's just the dh as a function of j, and I call this some function of j, whatever. It's just the derivative. And I'm going to identify this in a second, okay? Whatever this is, the solution of the equation of motion, this is still is just this new function nu time t plus some initial condition, okay? So it's very simple. What is the meaning of this nu? Well, from the symbol you can already guess, but let me compute the change of this little w over the period, over the full motion when it comes back. So I do the integral, right? And is partial of little w with respect to q dq, right? I go back to the dq coordinates through a cycle, okay? So you see this quantity, then I reintroduce the w, the big W, it's confusing, big W, dq dj, right, through this definition. And then I pull out the derivative with respect to j. So let me write it as a total derivative. And I have the cyclic, the integral of a cycle of dw big dq dq. But you see the derivative, the partial derivative of big W, that is the characteristic function with respect to q, is exactly the momentum, right? You remember? So this is exactly, well, let me write it, is the action variable. So in other words, you get 1. So maybe I should write it like this. This is P, therefore this is P dq, that is J, so this is 1. Is 1 because I only have 1 pairs of action angle variables, but it's going to be a delta, the Kroneker's delta, if you have more of those variables, okay? So you see that the change of this little w, right, that you see is over a period is nu tau, where tau is the period of motion, right? But this must be equal to 1. Therefore, you get that exactly this nu is the frequencies of the motion, okay? So if you have an explicit expression of this nu, right, you can compute that frequency immediately because you take dh, dj, okay, and you know that this is nu, right, the frequency. So if you have an expression for the Hamiltonian in terms of these action variables, just by taking the partial derivative, you can compute the frequency and therefore the period of the motion. So if you write your system in these new variables, you write your Hamiltonian, then just by taking derivative of your Hamiltonian with respect to the action variables, you can compute the period. That is what I said. So you have a formalism in which you don't have to solve any differential equations. You just write the Hamiltonian in terms of these new variables, and then just by taking partial derivative, you compute the periods. So it's very powerful. And for instance, for the harmonical oscillators that we just derived, right? This is the you see, this is the energy. So the Hamiltonian for the harmonical oscillator is just omega big J divided by this 2 pi, right, is what we computed here. So if I plug in there, I get the frequency is just the derivative of the Hamiltonian with respect to big J, omega 2 pi, that is exactly the frequency. Okay, in this case it's trivial, but, right? If I take the derivative, I get omega divided by 2 pi, that is in fact is the frequency of the motion, or in other words, omega is the, so 1 over 2 pi square root of k over m. Okay, so I've rediscovered what I already knew, but this was just an example, sort of very simple. And now I want to apply this technique to the Kepler's problem. Okay, so we are going to write the Hamilton-Jacobi equations for the Kepler's problem of the motion of a planet in a central force that goes like 1 over r square, okay? And this time we are not going to solve the differential equations to find the orbits like ellipses rather than circles, but I just want to find out what is the period of motion, okay? So what is the period for a planet to come back to the original position, okay? Can I erase? So this is one of the, I mean, most of the studies in classical mechanics, of course, they were developed for the study of the motion of planets, and therefore this was one of the tools that was used to derive these periods that they were relevant information, and it's rather elegant. So here we go. So Kepler's problem. You remember Kepler's problem, right? I hope. So what is the Hamiltonian for the Kepler's problem? Who wants to? So the Lagrangian, we wrote it several times. So knowing the Lagrangian, we can write the Hamiltonian. So it's going to be, the kinetic part is just going to be, so let me write it in space, 3 dimensions, okay? So it's the kinetic energy of a point particle, because the problem, well, actually it's the reduced mass, because you remember, right? You reduce the problem of the 2-body problems to the single problem. But okay, this is the reduced mass, but let's just assume that one is much heavier than the other, so it's essentially the mass of the planet moving around the sun. And then you write the kinetic energy in terms of the momenta. So this you should know by heart, that in spherical coordinates, so let me call P sub r is the momentum in the radial direction, right? P theta is the momentum in one of the theta coordinates, and then you have P phi square, that is r square sine square theta, minus, right, plus the potential that is minus r because it's attractive. So please try to memorize these kinetic energies, because otherwise you have to rederive it every time, and this is not very efficient. So knowing the Hamiltonian, I can now write the Hamilton-Jacobi equation, right, that we discussed last time. And actually, because I already see that we are in a situation in which there is no time dependence, I can use W as before, that is the characteristic Hamilton characteristic function rather than the action S, right? So what is the Hamilton-Jacobi equation? Well, sorry, 2m, I replace the momenta with the derivative of this characteristic function with respect to the conjugate canonical coordinates. So for PR is dWr square, and then I have 1 over r square dW d theta square plus 1 over r square sine square theta dW d phi square. This is the first part, minus k over r. And this, you remember, has to be a constant, right, in such a way that the full Hamilton-Jacobi equations can be satisfied. And so this is a constant that, well, you know that is the energy, so you can call it E, but you can call it alpha or whatever. So that's Hamilton Jacobi equation for the Kepler's problem. And again, how do I go about and solve this equation? Well, as I said, your only chance of solving such a differential equation non-numerically if you can factorize it, right? Meaning that this W in principle is an arbitrary function of the three coordinates, right? But in this form, it's very hard to. But let's assume that it's separable, meaning that it's actually the sum of three functions, each of which is a function of only one of the coordinates. So like this. You understand that this is the case, then this is going to be some constant, this is some constant, this is some constant, and these constants must combine to give you exactly that, okay? So, separation of variables. This is a general, probably you have studied that with Narayan. That's the general technique that you use for solving this differential equation with partial derivatives. I don't know if you have, but we will, when we discuss Maxwell equations next year, this is going to be very often the case. So because there you have equations that are of this form, and we will solve them using separation of variables. So this is the standard technique. And you see that if I plug in this separation of variables, this differential equation splits in three differential equations. Let's start from this one here. You see, you must have that, let's write it here, dw phi. So this is a function of only phi. So you want this to be a constant. You see, this is the only possibility if you want to have a solution here. And if this is true, then you can say that the w of theta, d theta, right, square actually, plus this term here, so plus, so I call this alpha of phi, so alpha of phi square divided by this sine square of theta. This again must be a constant. You see, you factorize. I mean, if this is a constant, then you factorize the part that has no R dependence, right? This must be a constant, and then whatever is left must be again a constant. Are you following, or one? Otherwise, I repeat. I mean, you want to solve this, so you see that if this is a function of only phi, okay, this is a constant, then the part of this equation that depends only on theta itself must be a constant in order to cancel exactly the part that depends on R. So this part is the part depending on theta, so that I call it alpha theta square is another constant. And then whatever is left is the only equation that I really need to solve. And you see that is this piece here, square, plus whatever this constant is that I call it alpha theta square, you see, divide by R square, okay, this must be equal to 2m E plus K over R, right? So my Hamilton-Jacobi splits in these three equations, 1, 2, and 3. Okay, so if this is my desire, then I can keep on going and solve these equations, and I'm going to rediscover what we already knew from the Lagrangian analysis that we did 1 month ago. But this is not what we want to do today. Now I introduce these action variables. You see, I have 3 action variables, right, because I have 3 coordinates. So let me introduce J phi. This is the action variable conjugate to phi. So by definition, this is the integral over a cycle, a period of a full cycle of motion. And I say the momenta, so the momenta here, you see, is defined as the partial derivative of the characteristic function with respect to phi, and you integrate over d phi. And j theta, just the same, with the theta. So what is this? Well, this is very simple because I'm solving these differential equations. Well, I'm not solving, I'm just using the fact that must be equal to a constant. So here I have a constant, right? So this is the integral of a constant over an angular variables, right? Over a cycle. So it's the integral over from 0 to 2 pi. So 2 pi, this constant alpha phi. So very simple. And j theta is a little more complicated because you see I have to use this. So I take this on the other side, I get the integral of the square root of alpha theta square minus this term that is alpha phi square divided by sin square theta. And I have to integrate over d theta. Actually, since we feel kind of lazy, I don't want to do this integral. And I use a trick. And the trick is that, remember that it is a motion in 3 dimensions, but if you remember, it takes place, because of the conservation of the angular momentum, it takes place in a plane, right? So I can always map this problem. In principle, is in 3 dimensions, but I can always, is actually taking place in a plane. So I can always identify polar coordinates such that we can describe the motions in 2 dimensions. That means that this is always true, that if I take P r dot, right, so I take this combination, is spherical coordinate, P theta theta dot plus P phi phi dot. So this is this quantity in 3 dimensions. It's always true that if this is in spherical, because of the conservation of angular momentum, this is, so PR r dot in this plane, and then I only need one angular variable that I call psi. This is in polar, because the orbit is taking place in a plane. So you see, this actually helps us here, because that means that you see, these two are the same, so that means that the P theta d theta, right, is equal, I take this on the other side, P psi d psi minus P phi d phi, right? So actually, if I don't want to do this integral, I can just replace here. Here is P theta d theta, but this must be equal to this P psi d psi minus P phi d phi. And these again are constants, right? Because this is the alpha and this is some other constant. So again, I guess just a constant that I can write as 2 pi alpha psi minus alpha phi. So what is the third angular action variables? Here we are running out of blackboard. Well, I guess I can, let me. J sub r, right, is the last one. I have to do an integral over my cyclic motion, and well, now I've erased exactly what I needed. Okay, I just it was written here, right? So you still have it, because dw right, you see that dw dr square plus alpha sub theta square equal to m e plus kr. And this is PR. So you take PR, take everything on the other side, and you see you have a square root to take. So if you do that, you get what I wrote here. You get 2me, just a constant, plus this term here. So let me write it 2m k over r. I want to keep the r dependence in evidence, because clearly I'm doing the integral with the r, plus something that goes like 1 over r square, right? That is this thing here. But what is alpha of theta? This was alpha of theta. You see that is minus, so let me write it j theta plus j phi square divided by 4 pi square r square, because I want alpha of theta, you see, can be written as, you see, alpha divided by 2 pi, you get the j phi, then you have this is the j theta here. So you can write alpha theta as j theta plus j phi, right? Divide by 4 pi square, I guess. No, divide by 2 pi. And here you have alpha theta square, so I put it here. And it comes with the minus because I have to take it on the other side. So, okay. So if I can do this integral, then I'm happy, because you see I'm going to get a relation between the energy and my action variables. And then as I take derivative of the energy, as I did for the harmonical oscillator, with respect to these action variables, I get the frequencies of the motion. So I've solved the motion. You see, I'm not solving any differential equation. Of course, as usual, it's not that I've solved all my problems. I still have to do some work. And in this case, the work is to do this integral. So any suggestion on how to do this integral? The book, right? But this time, I don't want to use the book, because I think it's time for you to review what you have done about the residues. You remember that these integrals you do by going into complex, on the complex plane. How beautiful. Did you enjoy that part of yes or no? That is one of the most beautiful. So I wanted to conclude by applying, at least once in your lifetime, that technique to a real example. So I want to do this integral, and I don't want to go and see the book. And so I do it the hard way. And how do I do it? So, you write it. So let me give a name to this stuff. So I call this A. These are constant. I only want the R dependence that is going to become a Z dependence in the complex plane. So I call this A, I guess. I call this 2B. And I call this thing here, okay, C. This is the same notation that you find in the Goldstein books. So if I go too quickly, then you can go back and see on your textbook there are all the same steps. So you see, if I go to the complex plane, I have this function here, right? Let me do it right. and I want to, I have to do this integral around a, so how is it? This is a square root, right? So you have two roots that I call R1 and R2. So, okay, this is the complex plane. The blackboard is the complex plane. And you see that I get, so let me try to do it right. So I go from R to Z, okay? So I have to do, so I consider this function, this minus, you see, it comes because I go to, of A plus 2B, now R is Z, minus C Z square, okay? So this is the function, this is the plane, this function has two roots, and this integral is from these 2 points, right? So if you wish, you go around like this, right? You go around like this, and this is this integral. And the nice thing about the complex plane is that you can, so this is kind of hard to do, but if you change your path, you pull it to the infinity, right? Presumably you have zero contribution from there, and as long as there are no poles around, then this is perfectly fine, okay? But of course there are two special points that is somewhere 0 here. So let me put the infinity here. You can always do that in the complex plane, right? To put the, and you see so that when you pull this, so this integral is equivalent to the integral, say, at the infinity that has no contribution, but you have the contribution of these two poles, and that's all the integral, because the theorem of the residues tells you that the value of this integral is the sum of the residues of around the poles of these functions. Okay, so you have two, and this is R0, the residues in 0. How much is that? You see, the residues is the coefficient of 1 over z, so you should look here. So it's minus c. Okay. So I guess if I go this way, this one goes this way here. No, if I go this way, when I pull it, this goes like this, and this goes like this. How about the infinity? You remember that to do that, you have to switch. You have to switch from z to 1 over z square, right? So, or in other words, you have to approximate this function. So you have, let's pull out the square root of a. Then you have square root of a, and let's pull out z square, right? Z. So you see what I'm saying? No, I'm just to compute the function at the infinity. You switch from z to z 1 over z. Okay. So this was this integral. So if I switch z over 1 over z, I get the z square here because I go from z to 1 over z. So dz, you get dz z square with the, okay? So I pull out then this term with the z square, and then whatever is inside, I do an expansion, 1 plus 2bz. So I'm pulling out the z square, so I have a 2a z plus other terms. And you see the pole now is this coefficient here, because the residues is always the coefficient of the 1 over z. So the residues at the infinite is whatever I have there, so I guess is minus, so I forgot, this is still a square root, so I'm expanding, so the 1 over 1/2 cancels the 2, so I have minus b square root of a. Okay. So that's a nice exercise for your mathematical method class. So I know that this integral must be equal to 2 pi I, the sum of the residues, and I have two of those, so I can write the result is 2 pi I minus square root of minus c minus b square root of a. I have done the integral magically. So I only need now to, so what is c? C was this coefficient here, right? But I have a minus here, so I get, let's see if I did it right. So c was this j, so I have the square root of minus c, so I have j theta plus j phi and 2 pi, right? But the 2 pi cancels this. I have a I, so it just, well, it's just this with the minus. And then I have the other term that it's b, so 2b was this, so it's mk over square root of a. So what I get? Huh? We don't?
We don't have the minus.
This?
Yeah.
Oh, is this one here?
We have
We have the I.
yeah.
So why do I have a minus?
Maybe the orientation.
So let me leave the minus because so you check. And b is there, so 2mb, so I have a pi, so the 2 goes away, and I have a square root of 2m divided by e, but the energy here, this is a bound motion, okay? So remember that the energy here should be negative. So let me write it as minus e, and then I have pulled out the I that gets rid of the other I. So now I can take, there should be a minus here because I know that the result is going to be just the sum of the j. So check, I made a mistake somewhere. Maybe, as you say, I went around the wrong way. So this is the energy. So the Hamiltonian, if you want, is equal to the energy. I take everything on the other side, and you see that I get minus 2 pi square. Okay. mk square, let's see if it's right, jr plus j theta plus j phi. Everything square. So I guess here I had a k, right?
Yeah.
K. So this is the same k. Okay? So I'm done now because I have my Hamiltonian in terms of my action variables, and as I said, the frequency are derivative of the Hamiltonian with respect to the action variables. And then the period of the motion is just 1 over nu. And you see that they enter symmetrically. So you only have one frequency of the motion. That is what you expect, in fact, is a closed orbit with just one period. So it doesn't matter. You can take the derivative with respect to any of the action variables. You see they enter in the same way. So if there is only one frequency of this motion, you can take a derivative of your Hamiltonian with respect to any of those. And you see when you take the derivative, you get 4 pi square mk square, and then downstairs you get this to the cube. And if I use, so then I can, you see, this is the energy, so I can rewrite this in terms of the energy, and I guess it's just minus 2e cube 1 over pi over k. So I use again this to rewrite this combination of the action variables in terms of the energy, and I get this. So the period of the motion, right, is 1 over this quantity, so it's pi over k, pi times k, m divided by minus 2e cube. If now you go back to your notes, and you remember that the semi-major axis of your ellipsis was minus k divided by 2e, then this period can be rewritten as 2 pi a, where a is this semi-major axis, 3 to the 3/2 times mk. So what is this law? That the period of the motion of the planet goes like 3.5 the semi-major axis, or in other words, the cube of the semi-major axis proportional to the square of the period of the motion. This is Kepler's, I don't remember, second or third law. That is exactly.
The areas required.
What?
The area.
No, that's the second or the first. I can never remember. This was a major observation by Kepler that if you map the semi-major axis against the period of the motion of the planets in the solar system, you fit this with this 3.5 law. This was a hint for the fact that they were ellipses. And here we rediscover these results in a, well, maybe complicated ways, but okay, that's what I wanted to show you as an application of the Hamilton-Jacobi equations by using these action angle variables that are what you are supposed to use if you are only interested in computing the period of a motion, not in solving the equations, okay?